All right, let's consider problem 7.20, which asks us, considering the Bohr model of the hydrogen atom, which of these transitions are considered to be absorption and which are emission? So let's talk about this a little bit, what we mean by the word transition and then this Bohr model for hydrogen, okay? So hopefully you've read the book or maybe been in lecture and you've heard this story about how Bohr came up with the model for how the hydrogen atom works. And it's kind of sort of a solar system model of sorts. And the way it really works pictorially, or the model for it, is that at the center of the hydrogen atom, we've got our nucleus, and hydrogen, of course, is element number one, so it's got a proton. So hence one positive charge there. And then the hydrogen atom itself has what? One electron, one proton, one electron. Okay, so there's an electron. So what do we do with that? Well, Bohr came up with the idea that that electron was allowed to reside in one of these concentric orbitals that are present in his model. And for lack of a better term, he gave them different numbers, different addresses where the electron could exist. Might it exist in the n equals 1 level, the n equals 2, the n equals 3, n equals 4, n equals 5? There's just a series of these concentric orbitals that the electron could exist in outside of the nucleus, okay? And the electron couldn't exist between the orbitals. It had to exist in one or the other, one of these integer numbered orbitals. But the electron was allowed to move between orbitals. So for instance, maybe the electron starts in number 1, but it ends up in number 4. Okay, well that's allowed. We can go from 1 to 4 as long as it's either in 1 or in 4. That's okay. That's sort of this quantized thing, okay? But we could move between orbitals without any trouble. All right. Now that movement of an electron from one orbital shell to another is referred to as a transition. So when I say which of these transitions are absorption, which are emission, that's what I'm talking about, moving an electron from one spot to another. But the thing is that if I'm going to move from one spot to another, that's not like a free process, okay? Sometimes we need to put energy into the atom. Now, where does that energy come from? Well, we learned earlier that the energy of a photon can be given by h nu. Turns out that if I shoot exactly the right frequency or wavelength of light on my atom, I can add a photon of energy to the atom, which provides the energy to bridge the gap between one orbital to another, should energy be required. Likewise, sometimes I can actually get energy back from the atom. I can have that atom give off light energy in the form of a photon. And again, it's a very specific frequency because there are very specific energy gaps between these levels. So let's kind of explore upon that a little bit more, okay? So beyond just this two-dimensional drawing of the Bohr model, I could basically plot out something that looks like this. This is an energy level diagram for these different orbitals, n equals 1, 2, 3, so on and so forth, okay? My y-axis here is energy, some measure of energy. Down here at the bottom is a line labeled n equals 1. That's for the electron residing in that lowest energy orbital. If I wanted to put the electron in there, I probably would draw a little arrow, okay, because the arrows represent the electrons in such diagram. Now, if the electron in hydrogen resides in that n equals 1 orbital, that's the one that's closest to the nucleus. Now remember, this electron is negatively charged, the nucleus is positively charged, so having those two charges together is kind of a good thing energetically, right, because they attract each other. So because of that, that n equals 1 orbital, that first orbital that's closest to the atom's nucleus, is lowest in energy. It's the lowest energy location that I can put my electron. Now chemists give that a special name. We call that the ground state. The lowest energy spot for that electron is the ground state. Here that's the n equals 1 Bohr orbital. There are other concentric orbitals that I said are also allowed addresses for the electron to exist. There's the n equals 2, n equals 3, 4, and 5, and so on, okay? Now all of these other orbitals, the 2, the 3, 4, 5, so on, are excited states because they are all higher in energy than the n equals 1. So if I'm going to move an electron from my ground state, my lowest energy state, to any one of these higher states, I'm going to have to pay an energy price. It's not going to want to do that by itself, okay? Now I can move an electron from my n equals 1 up to n equals 2. Maybe I can move it from n equals 1 to n equals 3 or so on, okay? But there's always this energy gap, or the delta E, energy price, that needs to be paid if I go from lower to higher. And guess what? That energy gap manifests itself as the energy of a photon. Okay, so the energy gap between two spots is the energy, corresponds to the energy of a photon that could be absorbed by this atom. So the atom absorbs the photon, takes in that energy, and then promotes an electron from the lowest energy level to one of the others. And in fact, you can move between 2 and 3 or 3 and 4 as well. It doesn't have to be 1, okay? The transitions from n equals 2 actually explain the emission in the visible region that Bohr used to generate this model. He worked with an emission spectrum, okay? Because that's what he could see from hydrogen atoms giving off light, okay? Now we talked about going from lower energy levels to higher energy levels, like 1 to 2, 2 to 3, and so on. If you go to a higher level from a lower level, that costs you energy, okay? That costs you energy. And when there is an energy cost, the atom must absorb light. The photon's going to be absorbed by the atom and used to go from a lower level to a higher. Okay? So what characterizes that is a lower n to a higher n. Cost you energy. Now what about the reverse process? Let's just say that might it be possible to go from a higher to a lower n? Let's just say that for whatever reason, my atom of hydrogen initially starts, the electron initially starts up here in n equals 3. Okay? And maybe that electron comes down to n equals 2, or maybe it starts in n equals 3, comes all the way back down to n equals 1. There's still an energy gap between n equals 3 and n equals 1. N equals 3 is the higher energy orbital compared to n equals 1. So I'm still going to need to bridge that energy gap, that delta E, and I still do that through a photon's energy. But if I go from higher to lower, the atom has to radiate or give off that energy. Okay? So in the case where energy is given off, the atom is going to be doing this through emission of a photon. So in this case, I have to go from a higher n to a lower n. If I do that, my atom's going to give off light, okay? That's what characterizes photon emission. Now because these horizontal lines, these energy levels that exist in the hydrogen atom model, are very specific energy levels, extremely specific. Not a lot of wiggle room with what their energies are, okay? Because they're so specific, and the electrons can only be here, or only be here, or only be here, or only be here. The electron's got to be in one of these concentric shells or these orbitals, and they have very specific energy. What that means is that the gap between any two levels, like n equals 2 and n equals 1, or n equals 4 and 3, n equals 3 and 2, the gap between any two levels is extremely, extremely specific or discrete as well. And what that means is that this atom will only absorb or emit, depending on the directionality of which way we're going, only to absorb or emit very, very, very specific wavelengths or frequencies of light that correspond to the energy gap that's required. Okay? So the hydrogen atom, is only going to give off or emit or absorb very, very specific energies or wavelengths. And the reason why this model was originally transformative for hydrogen is because it allowed the explanation of why hydrogen was observed to give off an emission spectrum of very, very specific wavelengths. This model explains that nicely, okay, in kind of a cartoon drawing sort of way. Now, this is really only applicable to hydrogen, this specific Bohr model. And the reasons why that are kind of rooted in the fundamental physics of it, okay? For hydrogen, it's nice because there's only one proton in the nucleus, and there's only one electron that surrounds that. Now, if you start going to other elements, things get a lot more complicated, okay? The main reason why that is because instead of just having one electron, now you're going to have 2 or 3 or 4 or 5 electrons. These electrons can interact with one another, which makes the physics of this a lot more difficult than if you've just got one electron and one proton. Also, even if you only have one electron in the orbitals, if you've got multiple protons, that can also change the allowed energy levels and change things up a little bit, okay? So this Bohr model really only works wonderfully well for hydrogen, to explain the line spectra of hydrogen, okay? All right, so back to the original problem. Now that we talked a lot about how this Bohr model works, I wanted to make sure you heard that story, because this question is extremely easy if you understand how the Bohr model works, right? So which of these transitions between the allowed orbitals are absorption, which are emission? Let's talk about this first one. In A, we go from the n equals 2 and we end up in the n equals 4. So the electron starts not in the n equals 1, but here in the n equals 2. And pictorially it goes up to 4. If I want to draw a picture of it up here in my energy level diagram, I would start in n equals 2, which is right here. And I'd promote that up to n equals 4. That's what we're talking about. Now, does that cost us energy, or do we get energy back? We're going from a lower to a higher. There's a cost. Because of that, this has to be absorption. Okay, so from lower to higher, it's got to be absorption. Let's talk about letter B. Now, letter B, we go from 3 to 1. This is a little bit different situation, right? Start off here in 3, come all the way down to n equals 1, our ground state. So we go from an excited state down to a ground state. That's a pretty big energy gap, and since we go from a higher energy state to a lower energy state, it looks like we get energy back. This is emission. All right? Higher to lower is emission. C, we go from 5 to 2. So we're way up here. Come down here. Looks like this is a very similar case to what we just considered. We also get energy back there. The way that the atom would radiate that energy to the outside world is it would radiate a photon, give off a photon in accordance with E is equal to h nu. Okay? This last one, we go from a lower to a higher. Clearly, that one's absorption. Because if you're going to go to a higher end, you got to pay the energy price. You do that through absorption of a photon. Okay? All right, so hopefully this was a useful description of the Bohr model. It works really good for hydrogen. However, if you start adding more electrons into the atom, things don't go as smoothly because the electrons interact with one another, and that creates differences in the allowed orbitals, if you want to think of it that way. Okay, so the situation is much more complex for multi-electron atoms.